All right, so I left this running for a while. So just to recap, we're running the ViZDoom reinforcement learning environment using a PyTorch machine learning model to drive the game to play the player. So it's going to learn to play on its own by simply playing the game. And to start with, it doesn't know what it's doing. And then by looking at the screen of the game and trying different buttons, eventually it learns, hopefully. Anyway, so up till now, what we did is we made a convolutional network model to take the input from the game and to produce an action. We sampled from that using a categorical distribution, and then we used the reinforced policy gradients algorithm to learn from that. And then we ran it, and it was random. Okay, so then I went off to run it, and so I came back after a couple of hours, and this is how it looked. So this is up to like 20,000 games, and it's still kind of random. So I was thinking maybe I need to add some changes, but then I went away for a couple of hours, ate some food, and I came back a bit later, and then it looked like, yeah, then it looked like this. Okay, so actually it learned. So what I'm plotting here is reward. So in the graph plot thing that I showed you before, that I wrote in front of you, it was plotting loss. This is plotting reward. So like positive is better, right? So all I did to change that was in the graph log, in the losses, which I didn't change the name. I simply changed loss to reward and then ran it, so we get this graph. So it's learned, and it learned pretty quickly because I think I started running it around 2 or 3 o'clock this afternoon, and now it's 6 o'clock. So it can't have taken more than about 4 hours. So that's pretty good, I think. I mean, I've had reinforcement learning algorithms that take days to learn, and this was like 4 hours. And we didn't. It's not even computerized, right? And the game runs pretty slowly, and so yeah, it was pretty fast. Um, yeah. I've modified this slightly to have this argument max episode, which lets me plot just the first 200 plus just the first 20,000 episodes to get that initial graph. This one, like this is up to episode 20,000, and then if I just like don't give that argument, then it plots like up to what is that 100,000, right? So basically, by 40,000 episodes, it had already learnt to play, which is pretty fast, especially because there's no batching going on. Like I would think, like a lot of time, like it might take 100,000 batches, and each batch is like 16 games or something like that, or even like a million sometimes. And here it's just like 40,000 episodes. So it's not even 40,000 batches. It's just like, I mean, if that was batch, that would be like 4,000, which is ridiculously small. So there we go. So it's learned. I guess we can plot the loss too. I didn't try plotting the loss since it actually worked. So let's plot the loss. So the loss should go down in theory, right? I mean, the loss should just be the flip, the graph. Oh, it's interesting. Wasn't expecting that. Interesting. Well, I totally wasn't expecting that graph. Yeah, I don't understand that. I'd have to have a think about that. Don't know why it's going up. I'll have a think about that. Anyway, the reward is going up. And has it gone up enough? I mean, basically, if it wins the game, it gets plus 100, but first it has to like move left or right to the right position, right? And the game is 160 wide, so I'm not sure how many times it would have to move left or right, but like I guess a few. Um, so basically, it's had to move like left or right about 30 or 40 times and then fire at the aliens. So I guess that kind of makes sense. I guess it would be kind of cool to see it after it's learned. So we should probably like make it save the model. So I guess we could do that. We could make it save the model every 10,000 episodes and then rerun it. And then we can load the model and try it. So let's do that. Other than that, like there were a few things I was thinking of doing if it hadn't actually learned. I mean, the thing is, it's always hard to tell when it's never going to learn, right? Because like, I mean, up to episode 20,000, like it looked like it was never going to learn, right? But like you just keep going, and then it has actually learned some stuff, just not well enough to actually see the difference yet. Um, so it's sort of like running like MCNC a long time ago, like Monte Carlo. What was it? I can't remember what it was called, but there was like in the years before neural nets, we used to do something called MCMC, and yeah, you would just go like this sort of stable state, and then it would flip every so often, but you would never know if or when it was going to flip. Like you didn't know if it was just never going to flip, or if you waited like 5 more minutes, it would flip. And this is sort of like the same way. But anyway, if it hadn't learned after, I guess I would have left it like a day or two. If it hadn't learned after a day or two, a few things that I would have done is firstly, so the moment we're doing a single episode and then back popping. Well, some of those episodes it wins and some of them it loses. So those gradients are going to be really unstable. So I feel that we would get more stable gradients if we back propped for 16 episodes and then did a gradient update, then did a weight update, a parameter update. So we only did a parameter update every say 16 episodes, and that way the gradients will be a lot more stable, and it will. I guess it will learn better, but I haven't tried. I mean, you can't tell these things until you try them. Another thing I would have done is I would have added entropy regularization, which just like makes it explore a little bit more. DeepMind uses that a lot. I believe it's used in the Atari paper. You know, I'm not sure if it's used in the Atari paper, but it's used in it's used in a bunch of papers. It's fairly standard. It's fairly easy to do, and it just helps it to explore, and it stabilizes the network. So it might learn a bit more slowly, but a little bit more stably. And what else? I would have tried initialization. Like sometimes when you initialize the parameters of the network modules, like the default initialization isn't always the best. So if you do like your own Xavier initialization, that often can learn faster. And what else? I might have played around with the convolutional network architecture a bit, like maybe added an extra linear layer, or maybe much more aggressively shrunk the size of the image of the input going in. So at the moment we're doing like convolutional layer, then max pooling, convolutional max pooling. I might have done an average pooling right at the start just to shrink that image right down to say 40 wide, 32 high, or something really tiny like that. Or like just printed that image and checked if it's like makes sense and I would be able to play the game from that image. And if I would, then just use that as the input because everything would just run much faster. There'd be fewer stuff for the model to learn. It would just be much easier. But didn't have to do that. All I had to do was let it run for hardly any time at all, like 3 hours maybe, and it's learned. So yeah, should we modify it so it actually saves the model out, and then we can run that again. And in the video after this, we can have a look at how that looks. So we don't want that. We want this Doom. So we're going to copy the ViZDoom part 5 into part 6. Right, not going to autocomplete, of course. We'll just make it save a model every 10,000 episodes, which seems like we look at the graph. 10,000 episodes is like long enough that I'm not going to have a zillion models, but I mean, I can just save the same model each time, right? But the thing is, like, saving models takes time sometimes. So let's just save every 10,000 and that should be cool. So basically, we've got our loop over episodes here. So basically, if the episode plus one modulus 10,000, oh, you know what? We've already done the plus one. If I modulus 10,000 is 0, then we're going to save it out. So we're going to do probably torch dot save. All right. So let's say save path. I'm just going to put it in ViZDoom model.pt. There's no arg path here, right? There's no arg paths here, so yeah, we'll just use that. All right, so torch dot save. I can never remember which way around this is. I guess we can. Oh, we didn't even install IPython. I guess we'll just. Oh, I guess I could just use Python, right? All right, so import torch, and then help torch dot save, or is it torch dot dump? All right, so which way around is it? It's the saved object first, and then the file like object second. All right, I never remember that because like pickle and torch is one way around. So all right, so here we're going to do net. I guess we can do the underscore dict. State underscore dict. All right, so state underscore dict, and is that a method? I can't remember. You know what? We're just gonna like save on the first one too, just in case I got it wrong. All right, so we're gonna save this out to save path, right? All right, so let's like check that actually runs. Um, so I'll just run it on my Mac briefly. So ViZDoom part 6. Did I save the part 5 to GitHub? I can't remember. Anyway, I'll do that after this. No. Oh, right, yeah. Model. Right, so it saved the model allegedly. Let's check. I kind of want to have IPython, but I think that takes ages to install. All right, so let's test that we can load the model. So import torch. We need to instantiate the network model, right? So Python path equal. Maybe we should. I guess we could just lazily like save the model, and then we don't have to hack around with like stuff. Like normally you should use the state dict because then it's less sensitive to changes in the model architecture and stuff. But here I'm just going to use torch.save without the state dict because then it's just easier to load. Although we're still going to have to import that actually. Let's think torch.load and then ViZDoom, what is it, model.pt. Yeah. You know, let's factorize the model out. So ViZDoom model.py. So we're going to take this network module. All right. I mean, I guess we could just leave it here and import it since we've got the guard, but it seems I'll just do it like this. All right. So here we want this. Do we need anything else? I'm not sure. All right. So here we're going to do from ViZDoom dot model import net, and then we're going to do touch ViZDoom indet. All right, let's check we can run that. So when we run this, we'll have to do Python path equal dot so that it can find the model. Right. What? Part 6. Interesting. Maybe we have to do like this. Oh, huh. So I called it ViZDoom. All right, let's call this right. So we can't have this in it. So let's do it. Let's call it ViZDoom lib, and we'll touch the ViZDoom underscore lib. Basically, the module I just created called ViZDoom, it hid the actual ViZDoom, so that's why it couldn't find Doom game in it, because my module ViZDoom didn't have Doom game in it, right? And so we'll move from our ViZDoom, we'll move the lodel into the ViZDoom lib. Right. Okay, and then we'll modify this to be from ViZDoom lib. All right. So hopefully that works. All right, so then we'll try rerunning. So Python path equal dot Python ViZDoom f, right? So let's get this. I guess we don't need it here. I don't know. Oops. Model. All right, so we need it back here too. All right, so it's saved, and then hopefully we can load that. So IPython. Oh, I need to do the Python path equal dot, right? All right, and then we'll do import torch. Model equal torch.load, and it was like ViZDoom model.p2. And that should be our model. All right, so that's our model. All right, so that hasn't really learned anything yet, but like we proved that we can load it. So what we'll do now is we're just going to run this. I mean, I'm going to go off and run it on my instance. And once it's learned again, we'll grab this, the saved model, and we'll run it with the game visible so we can see what it looks like. Yeah, so I'm just going to go off and run that. I mean, I can show you running it if you want. Oh, I stopped my instance. I guess I can just start my instance. I don't know if you really want to watch me start my instance. No idea. You don't have to use AWS. You can also use Google Cloud, for example. I just kind of like, I never really got into Google Cloud because it came later, right? So you can see I've got, oh, is it running? Oh, I left it running. Oh, it's running. Okay, so it's here. All right, so I can copy that up. Let's try that. All right, I should probably have done like exclude on PyCache too. I guess we'll just do that. Okay. Anyway, so it's copied the model. It's copied the ViZDoom part 6. Okay, so that's on the instance, and I'm already connected to the instance. So I should just be able to do part 6 and with a Python path. And hopefully that should go away. All right, so save the model. And it's just going to go away for 100,000 episodes. As you might have seen here, I'm using a C5.2x large. So that has like 8 cores, and well, we don't need nearly as much memory as it's got. But I just got like 8 cores. It seems to be able to use them. Runs quite fast. I'm just using that, and I always use Tmax on instances. All right, so yeah, there we go. So I'm going to leave that running. And then in the next video, I will load this model in after it's trained. I mean, we'll look at the graph after it's trained, or maybe it won't have trained, because like sometimes these are quite, sometimes they train, sometimes they don't. Like you get lucky, you don't. Or sometimes like this time it took like 50,000 episodes, right? But next time it might take 500,000, or it might never train. It's kind of unpredictable. There's a very high variance in the results. Anyway, once this is trained, or if it doesn't train, maybe I'll restart it or create another instance and start another one. Then I'll make a new video where I show what the game looks like when it's being played using this model. So hope to see you in the next video.